Hi, good morning. We're here on day 4 of the IGVC. We've just arrived at the site and we're doing some testing for the autonomous challenge, which is lane following and obstacle handles. You can handle delay, like a delay block.
Is this like a pre-can?
Now, the tent B, I would like to have coming back at 1:30, U of D, at 1:30 to 2, so at 2 o'clock Princeton, and at 2:30 Embry-Riddle. Once again, welcome to the playoffs.
We started working on Kratos this past February, so we really only had one academic semester to complete all of our work. Because of this, and because this is our first year in the competition, we aim to keep our designs simple, but innovative where necessary. We've been able to put together an advanced and reliable robotic system.
The first step in stereo obstacle detection is to capture an image from both of the cameras in the Bumblebee 2. We then use the camera's libraries to construct a 3D map of the environment based on the disparity between these two images. Finally, we implemented an algorithm developed at the University of California, Santa Cruz to detect obstacle points within this 3D cloud. We optimized this algorithm so that it could be run in real time, and we're able to achieve update rates of up to 10 Hz. The final output of the sense step is a cost map. This is actually a cost map we generated just this morning on the practice autonomous course. This contains both the obstacle and lane information from the sense step. After this cost map is complete, then we pass to the next step of our sense plan algorithm, which is planning. And John Mayer will talk about that.
And so because the world was already represented in cost map form, it made sense to reduce the path planning problem to a graph search problem. And that's exactly what we did. And we implemented the A-star graph search technique, which uses a heuristic to ensure that you expand as few nodes as required to complete an optimal search. And we used two heuristics. The first being the Manhattan distance heuristic. We found that this wasn't sufficient because when there was a clear path available to the goal, we weren't able to find necessarily a straight path. So we had a second tie-breaking heuristic that determined how straight a path was and rewarded paths that were more direct to the goal. And you can see shortly in the simulation on the right that as it comes around the left bend, it'll take a straight path to waypoint 0. Now, in addition to these improvements, we implemented an optimized binary heap behind our A-star implementation. Our binary heap was set up such that the update key operation, which normally takes O(n) time, took O log (n) time. And therefore, we were able to plan paths in about 20 milliseconds in a clear environment, about 100 milliseconds in a cluttered environment. Of course, once you have a path planned, you want to act upon it. And Gordon's going to come back up to talk about how we act.
Given these drive wheels, the speeds for these drive wheels, we use a low-level proportional interval controller to maintain the desired speed. And as you can see here, on your left is a predicted step response of our wheels, and on the right is the actual step response of the wheels. And you can see that they line up quite well.
Beginning with hardware, we used home-built Intel Core 2 Duo-based PCs and Gigabit Ethernet network. We used the LabJack UV9 data acquisition unit, which provides a message passing abstraction between all of our analog and digital inputs and outputs to our computers over Ethernet. We thought we could do a little better than Carnegie Mellon's IPC, which is implemented in C and doesn't take advantage of the object orientation of C++. And so we invented a C++ wrapper for IPC that we lovingly call IPC++. And here's how it works. First, You just describe a C-style structure with all the data elements you'd like in it. So in this case, we have a sample state estimation, northing, easting in the message. Then, on the publishing side, you simply declare an instance of that structure, populate the fields, and with one function call over TCP, reliably send that message to all interested subscribers on either computer. And on the subscriber side, it's just as easy. All you need is one function to handle the message, and one function to subscribe that handler function to the message you'd like to read. That's how easy IGVC is.
What is the makeup of your team in terms of discipline?
Well, the three of us here, I'm a mechanical engineer, I'm an electrical engineer.
Oh, that's me.
Okay.
So we have a wide range.
On your program, you said you looked at a number of options on deciding which operating system to use, and then I didn't get a good feel why you ended up picking Windows, given
So we picked Windows for a couple of reasons. First being just ease of use, everyone's familiar with it. Secondly, as you'll notice, we don't have any monitors on the robot. We use Microsoft's remote desktop product to do all of our interfacing with the robot. We found that was a lot easier to use than something like VNC or Linux distribution. That was the main reason. As I said, it definitely could run Linux. Most users. Also, I should add, we used Microsoft's Visual Studio for development, and Team Foundation servers are compatible with Visual Studio.
And one thing I'm going to point out is one of the problems with stereo vision is you have both a minimum detection distance where the field of view of the cameras don't overlap. You also have a maximum detection distance where the edges are identical. Our max range is 20 to 25 meters, which we felt was more than sufficient for this case. But the minimum range is about a meter. Luckily, one of the reasons we put the camera where we did is a meter brings us out to here. So anything that we can't detect, if it's in our field of view there, we've got bigger problems. So we've been able to optimize the sensor placement. In addition, all of our sensors, GPS, camera, compasses in here, and then two encoders on the wheels, these are all vertically aligned over the central pivot point of the vehicle. So all of our sensors have the same reference location.
Yeah, actually, to bring the robot out here from New Jersey, it wouldn't fit in the car with the sensor tower on. So it's just a handful of screws to take this off and line it on top of it. Very nice. Really good. And feel free to have a mint as a side. Our group, as you mentioned, is called Cave, so these are our cave.